Hi guys, so we're going to be going into modeling linear relationships and inequalities. So let's look at the situation. You have an option of buying $10 pies or $15 cakes, and you only have 60 bucks. So again, we have $10 pies and $15 cakes, and we only have $60. Okay. So what you just noticed is I just wrote in standard form um, a linear equation. Now, basically what's happening here is it possible that we could spend less than $60? Um, or, you know, does it have to be exactly? So normally, yes, this would be our equation, all right? 10 per pie, 15 per cake, and equaling 60 because we have 60 bucks. Now, is it possible not to spend all your money? Yes. Okay. Perhaps buying less? Of course. Okay. I would imagine it'd be much more difficult if you were to go out spending money at a store and you were told that you have to spend exactly $60. I mean, geez, that sounds kind of cruel. If it was more realistic, it'd probably be more on the lines of the, what about $55? I only spent 55. Okay, that could work. It's realistic. So normally, our graph, okay, if you're, and this is harkening back to the idea of intercepts, okay. So if you didn't want any pies, for example, okay, it'd be 10 times 0 because you do not want any pies, plus 15c equals 60 bucks. Okay, use the division property. And that means c equals 4. And that means 0, comma 4. Okay, because again, that's where you don't want any pies, you just want cakes. This means you can afford 4 cakes. Okay, um, so again, 0 pies, 4 cakes. Okay, and that's the coordinate right here. Now the other side of it is, what if you just want pies, no cakes? Your equation would be a little different. You would have 10 p plus 15c, but we don't want any cakes, so our c is going to be 0, and it's still going to equal 16, 60, okay, $60. So that'll cancel out. All you have left is 10p, $10 per pie equals 60 bucks, division property, and p equals 6. So this is again 0, sorry. This is 0 cakes. Okay, there we go. 0 cakes. And when you don't want any cakes, you can only afford 6 pies. Now in real life, we could spend less than that, right? What if you just wanted 1 pie and 2 cakes? You could afford that, okay? But how would we remodel this linear relationship to show that we're spending less than or equal to? So less than or equal to. So you should already be thinking, okay, isn't that an inequality idea? Yeah, it is. So instead of having 10p plus 15c equaling 60, it's going to be less than or equal to 60. That means it's an inequality. Now, if we're going to fix this graph to represent that inequality, if you tried this in Desmos, you would see a shaded region being created below your boundary line. Okay, and again, this right here is your boundary line. All right, so after the whole shaded region, basically, you would notice that any statement within the shaded region must be true. You can't afford 1 pie and 2 cakes. Okay, that would be a true solution. Okay, for that scenario. All right, so we took care of part C. Good there. Now, how would buying 2 pies and 2 cakes satisfy? Would 2 pies and 2 cakes satisfy this inequality? Well, let's check. 2 pies. Okay, there's 2 pies right there, and 2 cakes. Yeah, that works. That is a true statement. Here, let's try a different color scheme there. Yeah, that would work. That's true. Okay. Why? Okay, so yes. And they say why? Well, um, basically, you could also be harkening back to the ordered pair idea. Okay. So pi comma c. All right. In this case, it's more specifically 2 pies, 2 cakes is a solution since the ordered pair is in the shaded region. Give an example that would not satisfy the need to spend less than or equal to $60 worth. Okay, looking at my graph, if I bought 4 pies and 3 cakes, that would definitely be false. Okay, that would be way out of my spending area. Okay, so let's go ahead and show you that. If I spent again 4, 3, so I have 10 times p, and in this case I did 4 pies plus 15 per cake, and again for cakes I got 3. I'm actually testing this one algebraically just so you guys can see the statement. Is less than or equal to 60? Well, let's find out. That'll be 40, right? Four pies. Um, so that's $40, and 15 times 3 because we want 3 cakes, and that should give us 45. Again, less than or equal to 60, and oops, 80, silly me, 85. There we go. Is 85 less than 60? No, it's not even equal to. So that's why it's false. Okay. So again, that was for this idea. On the bound or not in the shaded region, not going to be a solution. It's not going to work. Okay, can't afford it. All right, number 2. So we have a different situation. All right, we have $5 hamburgers and $2 fries, but you only want to spend up to $10. Up to. Can we spend less than? Yeah. Can we spend exactly 10? Yeah. Okay. So writing a linear equation for the given situation, use H for hamburgers. Oh, we already did that, didn't we? Get in a habit of doing this, guys. All right, where you read the actual situation, underline the key important things. So we have 5H plus 2F, $2 per fry, is less than or equal to $10. Nice. All right, if we graph the following situation, we need to use our intercepts. So let's think about the crazy aspect of you just want hamburgers, you just want fries, okay? So as you can see here on our graph, we have hamburgers as our domain and french fries as our range, okay, just by looking at the axes. Now, if we want 0 hamburgers, how many fries can we get? So again, let's try that situation out. We want 0 hamburgers. How many fries can we afford? So let's use division property. And it looks like French fries less than or equal to 5. So that means 0, comma 5. If we plot that, it'll be right there. Again, this is the extreme aspect of one situation. Now let's try to find the other situation. You don't want any French fries, okay? So if we don't want any French fries, we're going to have 5h plus 2 times 0, because we do not want any French fries, less than or equal to $10. Division property kicks in. Yep, that's second time tonight. There we go. And it looks like h is less than or equal to 2. So we are at 2, comma 0, which is right. Yeah. And now the hardest thing to do for me is to try to draw a line through there. There we go. It's not perfect, but hey, what is? All right, so again, these are our two situations, all right? You don't want any hamburgers or you don't want any fries. And it gets you two ordered pairs, which are basically your x and y axes, and that will allow you to draw the line. Now, don't forget, we're graphing, and this is an inequality. That means we have a shaded region. So it's less than or equal to. So we're going to go below the boundary line. Okay, anywhere in this shaded region should work as true solutions. Okay, true statements. Solutions are true statements. Okay. Let's give an ordered pair that satisfies the condition of spending less than or equal to $10. Okay, this is coming close, but it looks like it'll work, right? One hamburger, two French fries. Already you're thinking, well, that's $5 for a hamburger. You want one, and you want two French fries, which are $2 per, and you want to spend less than or equal to $10. Well, that's just 5 for a burger, $4 for my fries, and 9 is less than 10. So yeah, that would be a true statement. This is a true statement. Okay, so in context, it's definitely going to be one hamburger and two fries. I'm hungry right now. I really want some In-N-Out. Raise your hand real quick if you want In-N-Out. You're going to get a high five. All right, part D. Would buying two hamburgers and a fry satisfy? Okay, two hamburgers. Again, hamburgers is your X, your domain, and fry is your Y, okay, your output, your range. All right, so let's go to 2, comma 1. Is that a true statement? No, it's outside the shaded region. So that's explaining why. So 2, comma 1, not within third time for today, within our shaded region. All right. So here's some more examples. And let me check your homework real quick. Okay, it's down there a little further. Let me go ahead and do this. This is more, the more you see this, the better. All right, so number 3, you are following this situation. You are a product manager of your company. You want to spend less than $20,000 for new equipment, okay? There's tablets, apparently you're buying for $200, and the laptops, which are $400. So label the axes to address two options in products. So let's see, we have tablets and laptops. Alrighty then. Now which one's cheaper? Tablets, right? So you could probably get more of them, right? So we're going to use the axis that has way higher numbers that could probably work a little bit better for us. So if we do that, we're going to have tablets down here. Okay. We could definitely afford more because they're cheaper than laptops, all right? And as for laptops, oh boy, I've never actually written sideways before. I don't think I can. Oh my goodness, I have never written sideways before. Okay, well, okay, here we go. Laptops. All right, so laptops is going to be our output, our y-axis, okay, in this situation. Now, if we're writing an inequality, let's go ahead and use T for tablets and L for laptops. Okay, let's see, we have tablets that cost 200 a piece, and, or plus, laptops, which are 400 a piece. Okay, I'm using L. And we want to spend less than is the keyword, not equal to, less than $20,000. Good to know, good to know. All right, so let's see. There's our inequality, and now we have to identify our x and y intercepts. That means our two situations where we don't want any tablets or we don't want any laptops. So let's say we don't want any tablets, okay? We're just like, you know what, no tablets. So again, if you're looking at our graph, we have tablets as our input and laptops as our output, okay? We're thinking about the situation here where we don't want any tablets, okay? So how many laptops can we afford? So let's do the math, all right? No tablets, so tablets are 0. And let's solve for how many laptops we can afford. Okay, so we're going to use division property. Again, the 200t gets completely decimated there because we don't care about tablets. And you should get for laptops is less than 50. Okay, so we have 0, comma 50 for that one crazy situation. So that'll be right here. Okay. Now let's solve for our tablets. Let's say we don't want any laptops. We got some people who like to walk around, okay, and they just want to have tablets for work. Okay, so let's try that out. Again, if we do that, again, laptops is going to be 0. Let's solve for tablets. So let me try to find some more room here. I'll work down here. So again, we don't want $200 per tablet. We don't want any laptops. Okay. But we still have to spend less than 20,000. Okay. Let's use the division property. And it looks like t is going to be less than, you can cross out, cancel those zeros, 100, less than 100, just right here. So 100, comma 0. Told you we could afford way more tablets. They're way cheaper, right? They're literally half the price of laptops, and that makes sense because 50 is half of 100. Okay, that worked out nice. But notice it's less than. So if we were to graph in part D, is this going to be a dotted or solid boundary line? It's going to be dotted, okay? It's got to be less than, okay? Less than. So less than means that we shade below. Nice. Okay, anywhere within there can work in terms of money. That's very good to know. It's within our budget. Now they're asking, would buying 25 tablets, okay, let's get a coordinate system here, 25 tablets and 50 laptops be within our company's budget? So let's look at our graph. And I've actually seen these for work. People do this for businesses. They literally go, hey, we can't afford this. This is outside our profit margin or within our budget. All right, so here we go. Governments do this too. All right. That would be that situation. Is that within the boundary line? No, that's false. Epic fail. All right. So no, 25 comma 50, not within the shaded region. Okay, if you were to actually look at it algebraically, it'd still be a false statement. Okay, you could always double check again using the original equation. 200 per tablets. You want 25 of them. You want $400 per laptop. You're spending 50 on them, and you want to be less than 2,000 or 20,000. And ultimately, what's going to happen is it's going to give you a false statement. Okay. All right, would buying 50 tablets and 25 laptops be under your budget, and why? So let's go to 50, comma 25. 50, comma 25. Ooh, that is actually right on the boundary line. And that's the fourth one for today. So here I'll use black right here. There we go. 50, comma 25. That is right there on the boundary line, isn't it? So wow, that's 2 times in a row. 2 times in a row. That's number 6 right there. Wow. Number 7 straight in a row. Oh, technology. Why you do this? Why you do this? There we go. Now it's less than, right? So if you notice, if you bought 50 tablets and 25 laptops, you're spending exactly $20,000, but you want to spend less than that. So that too is false. And that's because the boundary line, okay, is dotted. Okay, that's a big deal because it's on the boundary line. All right, graph both inequalities. All right, so this is number 4. Okay. Graph both inequalities and answer the following. So let's see, what's my B? That's here. Down to, again, this is my rate of change. So it's down 2 over 1, down 2 over 1, down 2 over 1. Is it dotted or solid? That is dotted. Okay, so dotted line. There we go. All right, g of x. So again, this was f of x. Let's label them. Let's also color code them. That way you can differentiate. G of x, what's my b? My y-intercept, right? And, ooh, I think green does not work well for your guys' screen, so I'm going to use this nice pink. Yeah, I think green is hard to see on a computer screen. Oh, it still did not work. Oh, wait, there it is. Okay, sweet. Okay, so there's my intercept and my slope, my rate of change. Okay, down 3 over 1. Dotted or solid? Solid. Boundary line. Okay, so I'm going to draw. There we go. Okay, shading. Where do we shade? So the red guy, let's take a look. Red guy. Red guy says f of x is below or less than, so we're going to shade below. Notice how I'm not really caring about the g of x. I'm not worried about g of x. G of x is doing its own thing. As long as I'm below f of x, everything should be hunky-dory. Everything should be just fine. Okay, so now let's graph or shade for g of x. Again, it's less than or equal to. That means we shade below g of x. Again, g of x is the pink guy. Nice. All right. Would both f of x and g of x have a solution of 0, 6? So if we use the graph, 0, 6 would be right here. It's actually on the boundary line of f of x, but it's dotted. So no, and it's nowhere near g of x. So no. It's again, it's 0, 6, not within either shaded regions. And if you look at the boundary line for f of x, it's dotted, so no. Okay, that's false. All right, would both f of x and g of x have a solution of 1, 3? Let's take a look. So 1, 3. Oh, it's true for f of x, but it's false for g of x. You guys see how it's under f of x, but not g of x, nowhere near. All right, so f of x, yes. G of x, no. Okay, and again, it's because it's true for f of x, but it's not within g of x's shaded regions. Okay, and that's the explanation. I'm just doing that one verbally. All right, would both f of x and g of x have a solution of 3, 0? Let's take a look. 3, 0. No, for neither. And it's very similar to part A. Okay. They're not in the shaded region, and it's on the boundary line for f of x, but the boundary line is dotted, so no. Okay. Now, a good place for it to be a solution for both would be like 0, 1. That would be true for both f of x and g of x. Okay, that would work for both of those functions. All right. So the rest of it is just homework. Number 1 is very much like the last problem we just did. It's just asking you, is this guy a solution? Is this guy not? So get that good conversation with your groups. Number 2, I kid you not, this is a good problem. It's a real good problem. Work together on it. Try to graph it, get that conversation going with each other, and see what is realistic and what's happening at the moment with our planet. All right. Have a great day, guys, and let me know if you have any questions.